Welcome again to Building Stuff, continuing our series on Tesla coil testing, tuning, tweaking, and building certain components. So we're going to, I'm going to show you how I'm going to build a new rotary spark gap today. And we're going to be using one of these old cordless drills from the back from a few years ago, which used a NiCad battery, and they died quite rapidly, unlike the new lithium-ion batteries that we have today. So inside is quite a reasonable 12-volt or 18-volt motor, and we're going to use that. Now let's have a look at the old rotary gaps that we've made in the past. Here's one of them. Motor is a little bit smaller in comparison, but it should do the job. This is one of the other rotary spark gaps, very similar in design. And again, another rotary spark gap, similar design. Okay, so this is the rotary spark gap of the 220 nanofarad capacitor dual microwave transformer Tesla coil. These contacts using the bolts with the tips machined so that they came to a narrower point, so for a small contact. And what happens is that it glows red after a short operation, and it burns the contact, and so the spacing of the contact is increasing as time goes by, and it's damaging the bolts there, as you can see. So not the ideal design. It doesn't last very long in this way. The other spark gaps, rotary spark gaps, have the nut end or the hex end facing each other, presenting a larger surface area, and so they don't heat up as badly and burn so easily. So this is going to be our fourth rotary spark gap. Let's get to it. Right, planetary gearbox that drives the chuck. We keep that for perhaps future use for another project. Switch and driver circuits and the motor. We're going to keep the little screws for mounting, and we've got that with the pinion gear there, and we're going to use that. Now let's have a look at the design of the previous rotary spark gaps in detail to give us an idea of what we want to achieve in the new one. Motor drives a rotor with 8 stainless steel bolts on it, each of these being 6mm diameter bolts on this side, 8mm diameter bolt. And you can see in this Tesla coil, which uses 220 nanofarad, which is quite a big capacitor, it discharges a lot of energy across the spark gap, and it burns it as you use it, and this glows red hot. What we want to do in the next one is try and create a rotary spark gap which is firstly simpler to build, and secondly might resist some of that burning of the electrodes, even with a high current discharge using high capacitor banks. Now what we're going to use is some TIG welding electrodes made out of tungsten. Now tungsten can handle extreme temperatures in excess of 3000 degrees, and it's used for generating the arc for TIG welding. And if you do any TIG welding, you'll know that. I have some of these lying around for my TIG welder. Now you can get these from welding stores, and you may be able to get them in a larger diameter, but it's not a very big electrode. So what I might do is I'm going to see if I can use 3 of them and allow the current to be carried through more of them at the same time. Just back to the design of the previous spark gaps. Now you'll see that the rotor has the 8 contacts or bolts on it. That's hurtling through space, and it's self-cooling, and there's these fins that are helping to blow air over and cool the static side of the spark gap. However, because there's 8 on the rotating on the rotor, that's sharing the heat load as it's rotating, as well as cooling very efficiently as it's hurtling through space there. Whereas these sides, although the bolts are bigger, they don't have the benefit, only this fin trying to blow air over it, but it's taking all of the current every time these other ones make contact. But these are sharing the cycle or the cyclic load, the duty cycle effectively, and so these are heating up and glowing red hot. So we want to change that arrangement in the new rotary spark gap, and you'll see how that's done. Now I'm drilling a bit of aluminium. It's 10 millimeters wide by about 34 millimeters by 20 millimeters. And now the exact dimensions don't have to be the same as that. can be adaptive to whatever motor you're using. This is going to form the basis of the shaft adapter. It's going to attach to the shaft and make connection to that motor in that, via the shaft. Now you will want to use a drill press that has a compound slide so you can accurately mount your vise and then drill accurately your positions in order to get an accurate fit. Because if you introduce any eccentricities, you're going to have problems with vibration when the motor is rotating. So drilling things symmetrically as well is very important. Now I've tapped screw holes which will allow the screws to tighten onto the motor pinion gear to lock it in place. So that's the adapter. And I've cut a piece of acrylic 10 millimeters thick and a bit wider. That's about 30 millimeters or so wide by about 35 millimeters wide. And now I've drilled a hole through that and I've secured it to the aluminium piece. That will allow me to drill holes in here and all the way through to line up for screw holes to affix them together. And that center bolt is going to hold everything concentric or in line with each other until such times as the new screws go in. So I've drilled that hole in the aluminium, countersunk it, and removed that and tapped the plastic or the acrylic underneath and secured the screw in there. And I'm about to do the same on the other side, symmetrically, diagonally positioned. Now I've drilled 3 holes in the acrylic for those electrodes. Now why 3? Remember, we're working with high frequency and the skin effect. Those electrodes are quite small in diameter, only 3.2 millimeters in diameter. So you want a lot of surface area to carry the current. That's one thing. And 3 of them being spaced apart, will allow air to pass between them and cool the electrodes as they're moving as well. But if you can get one big thick electrode, then that would probably save you the work of drilling 3 holes. What I've got is just these 3.2 millimeters, so that's what I'm going with and doing it this way. So that's how the 3 electrodes will sit. They're sliding in and out at the moment. So what we're going to do is to create some screw holes and tap the acrylic on either side here and here to secure the top 2 in place, and the lower one will be secured down by a hole in the middle from the top here down. So there we have it, our electrodes on the shaft adapter for the motor. Holes drilled on the side, tapped and screwed to secure those electrodes in place from the 2 sides for the 2 upper ones and from the top for the lower one. Ready to go. Just need some grub screws in there to lock it onto that pinion gear. Now we need to plan the plate on which we're going to mount the motor and all of the 8 static spark gaps. So measuring across there about 22 centimeters, we'll make it 25 centimeters of the plate to give it plenty of tolerance to work with. Okay, so we've got ourselves a acrylic plate, 6 millimeter thick, for mounting all the components of the spark gap assembly. The thing is, because of the motor that I've chosen, the spindle is not very long. It won't protrude through the 6 millimeter thick acrylic. So what I'm having to do is drilling a big hole through the center to allow the motor to sit through, and then using a bit of aluminium, thinner aluminium plate, 3 millimeter plate, drilling mounting holes, 4 mounting holes to screw it onto the acrylic, and center hole for the motor to poke through, and screw holes also countersunk in order to recess the screws down so they don't interfere with the rotation of the adapter that goes onto the spindle. Let's assemble that. So now we have our mounting plate for our motor and the aluminium plate, holes drilled here to secure that aluminium plate down to the main base plate, and our spindle with the tungsten electrodes. Now we can figure out how high off the base plate to place our other static electrodes. Right, now we're going to make 8 static spark gap mounting brackets. In order to do that, I've clamped a stop here to make reproducible cuts so I don't have to measure every time. Just bring it up against there and make the cut. Right, 8 mounting brackets for the static spark gap. And we're going to do a quick drilling protocol for mounting them. Going to set the
mil drill to drill, line it up and do 8, and then do the second hole in the same position and lining it up with the edge of the vise there. Okay, it's about 2 centimeters from the bottom of the mounting plate to the middle of those 3 electrodes. So we're going to want to drill the bracket for the static electrodes 2.5 centimeters from the bottom, and then tap those to put these stainless steel bolts in to use as the static electrodes. Okay, we've drilled the hole appropriate for tapping with the 12mm metric 12mm tap. So while it's in the machine, the piece is in the machine, we're going to tap, set the drill to slow rotation and tap using the machine. Okay, so the machine has tapped that nicely, checking that the bolt fits, and repeat for the other 7. Okay, so we've drilled and tapped all of the holes for the 12mm static spark gap bolts. Now we're ready to measure for their screw hole drilling positions. So we've set these things up roughly, and we're going to give a little bit of spark gap distance and a little bit of adjustment away from the spark gap, and then later on the bolt can be advanced further out as the electrode wears out with use. So I'm just going to mark the position down here, measure from the circle from the circle there, and repeat for all of the others. And it's not important that it's exceedingly accurate, because there is a tolerance and adjustment in those bolts, and so you can adjust the gap appropriately. Right, we've got our mini Stonehenge happening here. The fixed electrodes are all assembled, and lock nuts in place for once you've adjusted the position. Then you can lock them in place. A vibration won't cause them to move, and once adjusted, everything should be working pretty well. Okay, so we've just got to tie 4 of them together on each side with connectors so that they can form the electrical circuit. Right, our rotary spark gap all wired up, ready to be used. Motor needs connection with a motor speed controller, but other than that, ready to go. That's taken me about 5 hours to accomplish a high quality rotary spark gap there. It might take you a little bit longer, especially if you don't have the materials at hand and not familiar with the workflow, but a great outcome, and something that you can try. Well, thank you again for watching. Please stay tuned, please subscribe and like, and at the next video I'm going to show you the entire assembly of the single MOT microwave oven transformer Tesla coil to get it to this point. And perhaps in a video just before that, I might do a safety related video in regards how to work with high voltage safely. So stay tuned.